Okay, great. Thank you, everybody. Once again, I'm so sorry to not be able to be there in person, but I'm really excited to share this recent work on Leximax approximations and representative cohort selection. And so this is joint work with Monica, Charlotte, and Omer. So in a variety of settings, you might want a cohort, and you might want one that is representative. And so, for example, in a consumer panel, what you might want is a subset of your general consumer base that you can understand their different needs. And what you might want is a good representation from different markets, different segments of the market. And similarly, in surveys, you can imagine if you don't have resources to survey a very large group, you might do your holistic user surveys on a small representative group. And increasingly, in cases like civic participation committees, cohorts of people are being either selected or volunteered to make decisions on behalf of a larger city where you might want to get good representation for different groups. And so I've glossed through these examples using words like representation and diversity. And so diversity can actually mean a lot of different things in different contexts. So for example, you can think of diversity, for example, in search queries can mean very different things than in this setting as what we're talking about in a representative cohort. And so one first example that comes to mind, if you take a stab at what you can consider as diversity, is maybe we just want a representative from every subgroup in the population. Okay, well, so this guarantees that every subgroup is represented and that variations of this notion, so we can have some kind of proportional representation for subgroups of the population, have been studied in various previous work. But this kind of notion also does have its drawbacks. For example, you might get a token member. So if you're at an intersection of identities, maybe you technically are on the cohort and you've covered every subgroup, but you don't have the decision-making power that you would like. Or another issue is, I guess, related to the talk before, is this is a very discrete notion of representation. So you're either a part of the subgroup or you're not. So you either do or you don't represent the subgroup. And we know that people contain multitudes and subgroups do as well. And so there might be different interests represented by different potential candidates that is not well summarized by just membership. And I think lastly, and most importantly, oftentimes we describe diversity as a top-down singular objective. So as an institution or decision maker, they ask just the yes or no question, is this diverse, is it not diverse? And when we want to accomplish goals such as representing different individuals or subgroups as well as we can imagine this is naturally a multi-objective problem. And so in our work, we really want to motivate, we're really motivated by this definition that we want good representation of every subgroup in the population. And so in this talk, I'll go through 3 sections. I'll go through a fun problem formulation, and then I will talk about notions of approximate Leximax, and then I will conclude by quickly going over some ways to find Leximax cohorts. Okay, so problem formulation. So let's say we want to create an environmental action committee, and we have candidates and we have the population. And so in this example, you can think of the population as either different subgroups or different individuals. And what's important is that you can imagine candidates will represent the interests of different subgroups to different degrees. For example, maybe you care about Arctic interests, and polar bear group will obviously be very well represented by the polar bear candidate, but maybe also somewhat speaks to other subgroups as well, shown in the dash arrows here. You could have other interests, for example, that multiple candidates might represent a subgroup's interests, or multiple subgroups might be represented by a single candidate. And in this case, here's a case of membership where I guess whales are technically mammals, but maybe this whale group feels none of these candidates really represent their interests, and that's okay as well. This really shows the flexibility of something like this. And of course, we have some niche notions, such as being a bear, that can only be represented by a bear. Okay, so if we aggregate all the preferences, what we have is some notion of utility of each candidate for each subgroup or each individual in the population. So this utility is a utility of representation. It is how well this candidate represents me and my interests, or my subgroup and our interests. And so a natural question that arises is, if we have different subgroups or different individuals in the population, how do we trade off these utilities? And so, for example, as I said, we can have utilities across each group, between each subgroup and each candidate. And so one thing that might come to mind is, okay, why don't we just maximize the utility of the worst off group? This makes sense, and here's an example. So in this case, the max-min solution is going to be picking our polar bear as the candidate, because for the worst off group, we achieve the best value. And so, but perhaps what if the worst off group is the same? And so this is an example here. So if the worst off group is the same, how do we distinguish between which solution is better? And as the title suggests and the outline suggests, one notion that we think makes a lot of sense is, if we want to maximize representation, we can think about this lexicographically maximal objective. So we want to identify the solutions that maximize the utility of the worst off group, and then within these solutions, then identify solutions that maximize the second worst off group, and so on and so forth until all groups have been considered. And so this objective finds the best possible guarantees for all groups and not just the worst off. And you see that it's pareto-optimal compared to the max-min objective. So why not use this lovely definition? Well, for one thing, finding optimal values can actually be very difficult. As you might have already guessed, now you're thinking about your solutions for different groups really depend on what you narrow down the solution space to in the worst off group and the second worst off group, and so on. And additionally, it is very sensitive to low utility values. So here's an example. Let's say now we have one very unhappy penguin in our example. For all the candidates, this penguin feels not very well represented. But if it is slightly better on one candidate, such that for all the other subgroups, they're not represented well, this actually unhappy penguin can determine really unilaterally which solution is lexicographically maximal. And so what we might want, perhaps, is in this case where we're estimating how well groups are being represented, you can imagine there could be noise, there could be systematic noise. And so maybe small variations of the values shouldn't lead to way worse outcomes. So let's say we say, if we do say variations within 0.01, for example, is just noise, then we can achieve much better outcomes for the rest of the group. And you notice that, so our goal here is to find an approximate definition that preserves our semantic meaning of Leximax. So we do want to do as well as we can for every group, starting with the worst off group, but we also want to be robust to small variations in utility. And so now I'll talk about different notions of approximate Leximax. So our naive first try is, okay, given a Leximax solution, let's say this is a vector of utilities that is lexicographically maximal, why don't we just use an element-wise approximation? So element-wise just means that we will give a little, we will have some wiggle room in each value such that it's somewhat close to the actual Leximax optimum. But this is actually a very strong requirement, since very small changes in worst off groups can eliminate or include solutions that vastly differ in other groups. And when you're not actually given the Leximax optimal, because you are trying to find it, this ends up being very difficult. So in the single objective case, we see that notions of approximation are straightforward, but if we look at this element-wise approximation for a multi-objective case, we see that some of these actually pretty simple notions become very difficult to achieve. And so one really promising notion from previous work, I think by some authors attending here, is this idea of a recursive approach. So prior work focused on this learning problem of looking at errors for a classifier. And they consider a set of possible hypotheses with different errors for each group and reduce the set to be approximately Leximax. And so the question you can that you can answer is, what kinds of solutions are possible if there's a small estimation error at each step? So for example, given a small slack for distance to the Leximax value of the worst off group, you can reduce the possible set of possible hypotheses to those that are within this slight deviation. And note that this might lead to the best attainable values for the other groups to decrease, since you're now reducing the set of solutions. And so you can now repeat this across all the other groups. And one thing to note that small errors can, while recursively computing this Leximax solution, can lead to drastic different outputs. And so, great. So now we have this recursive approach. But maybe what's not as clear is, what does it mean semantically for us? So our original goal was to be as close to Leximax as possible, or to guarantee the best possible outcome from the worst group onwards. Well, in our work, we think and explore other notions that might make sense semantically. So one other notion is this. So let's say that if we do have an approximation, it is a good approximation if any other solution that significantly improves some group's utility must also decrease the utility of a worse off group. So more formally, for solution S, if there is an alternative solution S prime that improves some group's utility, then that alternate solution must also decrease the utility of a worse off group. And intuitively, what we're saying is, if we can't trivially increase the utility of some groups without decreasing of other worse off groups, then what we have is we've already arrived at solution S, which is a good trade-off approximation. And so what's interesting is that slight alterations to this definition, we prove in our paper, results in no solutions very quickly. And what's also really interesting is that we prove that this is actually essentially equivalent to the recursive approximation we define above. So semantically, it feels very different in terms of this notion of trade-off, but we can prove that it's actually, for the purposes of this presentation, equivalent. And for the finer nuances and details, you can see our paper. So a second notion of approximation we explore is, how can we find these approximations that improve the exact Leximax solution? So in this case, where we have these tensions between different subgroups trying to maximize utility for with different candidates, we can ask, can we significantly improve another group at a very small cost from a worst off group? And this is the example here. So if for the Arctic fox, we can slightly decrease its utility, we might be able to increase the utility of other groups. And so this is just a snapshot of all of the utility matrix for just these four. And so this is the idea behind significant recursive approximation as a definition that we introduce in our work. And so formally, this is a solution that significantly improves some groups' utility while ignoring slight decreases of utility in worse off groups. And so I've talked now about a few definitions, and for the last part of this talk, I wanted to talk about finding these Leximax cohorts. And so as you can imagine, finding exact cohorts is a combinatorial problem. So for the relaxed version of the problem, what we do is we can directly formulate this problem into a linear program where we relax the integer constraints into fractional cohort membership. And so what we get is a distribution over how likely each individual is to be in the cohort, and we can sample over that. And so the key here is we just minimize, we maximize the utility that sums of groups achieve sequentially. So we first maximize the worst off, we first maximize A group's utility across all groups, and then we maximize groups of two utilities across all groups, and so on and so forth. And so you see, this is like an exponential number of constraints, but fortunately, we can directly solve this in polynomial time using ellipsoid method with a separation oracle that runs linearly. And for the mixed integer program part of this problem, just for the max-min setting, so we only want to maximize the utility of the minimum group. So for k greater than 1, so for larger cohorts, the max-min version of this problem is actually hard. And so this gives us a sense of why this problem is difficult. And so for the main takeaways of this talk, what we really want to say is, okay, so in this cohort selection where we want to maximize diversity and representation, what really makes sense is this flexible representation of utilities. And we can trade off these utilities by this definition of lexicographically maximal utilities. And finding these solutions that are robust leads us to explore different approximate notions. And so we talked about two quickly in this presentation, but we have more in our paper that we can direct you to. And so future work might include approximate notions based on multiplicative error, other functions of group utility beyond linear utilities, or as I said, a lot of this was about really pleasing one unhappy penguin. So you can imagine if you incorporate strategic manipulation, you might arrive at a much more difficult problem. So great, thank you everybody for listening.
So let's thank Judy again.